on a distributed generation is a solar. If all of our houses that we live in have solar, if this campus, with all these buildings that they have, if they put solar on the roof, they can satisfy their needs, or at least 50% of it, or 60% of their needs. And if the power plant goes down, 60% of a campus can be operated by the solar. So we don't have to be indoor. We can shut the lights off a little bit, turn the air conditioning down a little bit, and turn off all the non-essential, non-important things for that period of time until the power comes back on. So distributed generation is a solution. For that, we need a smart grid, which we're going to talk about. Now, the power transmission, we talk about generation up to now. Now we're going to talk about transmission. The power transmission is when you have a generation facility, this is where power is generated. Then it goes in these towers that you've probably seen around Long Beach. It's a structure that is, it's up about 50, 60 feet up in the air. And they usually have 3, sometimes 6 lines on those. Those are the cable that they carry in the power. The power from this station comes in a very, very high voltage and high ampere. And will be carried through this transmission line, and it comes to what we call substation. So all this power on the transmission line, it comes to the big, huge station that it's called receiving station. They get all the power from different transmission lines. Then, from there, what we call step-down transformer. Most of this power coming on the transmission line is a 500,000 volt and a 3,000 amp. This is a huge power. What we use here is 110 volt, and the amperage for this room is 30 amp. So compare these with those numbers. If you have that much power coming to this room, everything in this room is going to be melted. All your computers, the light fixtures, everything. And it's going to catch fire. They're all going to get melted. So the way we do it is, this comes to a huge station, and then there's a device called transformer. Transformer's job is to step down this high voltage, to bring it to a lower voltage for distribution, and then when it comes to our house, there is another transformer to further step it down so we can use it. So that's the concept, is the transmission line carrying a very high voltage, then distribution line carrying smaller voltage, which we call medium voltage. These are high voltage, medium voltage, and low voltage comes to our house, which is 110 or sometimes 240 volts.
I have a question here.
Sure.
What is such a high temperature? I mean, can you use that?
Generally, when you have a 1500 megawatt of power, that would be the voltage and ampere coming through the line. When we build a Utah power plant, we bring in 1500, actually 3000 megawatt of power from Delta, Utah to Los Angeles through the HVDC high voltage grid current. And then bringing it back to AC on the same voltage.
That's a lot of power loss.
It is. It is. And then Then we're going to bring it to the distribution station or receiving station that has the ability to get that. In that station, we have like 20, 30 transformers to step it down to basically 66 kV, 66,038 kV, and 12 kV. That goes through the distribution system. And this distribution, when it comes like to the campus, this is when it comes to this campus, 66 kV. And then there are so many step-down transformers for every building that they step it down to 480. That's when it comes inside the building. Then from 480, they go to 110 or 120, basically, to distribute it inside the campus. So that is basically, the whole concept. Now, we have large customers, for instance, manufacturers, mining companies, railroad companies, a metro, that you take a metro lane going back and forth, they use a lot of power. So some of those, what we call primary customer, we give them power in a higher voltage. So they have their own transformer to step it down for their needs. But the regular average customers like us, like this campus again is a large customer. It gets a higher voltage than your house, my house, or a small place that you get hamburger or Subway or sandwich. So that is basically, in very general idea, that's how the transition. By the way, these are the towers that I was talking to you about. You've seen this a lot. Each line carrying one phase. These powers come through AC or alternate current, and it has 3 phases. So 3 phases, you have 3 lines coming through the transmission tower. Now, these transmission towers, they're all connected together. That's what we call power grid. So just imagine that, the western states, it's all like a grid like this, that we're all connected. We're connected from Washington, Oregon, Idaho, California, Arizona, Nevada, Utah, all the way to Colorado, Wyoming, Montana, and portion of Texas. This is the western region grid. Then we have Midwest that has north and south, and then we have east that has north and south. Also, those are the grid that everything's connected. Now, to control those transmission, we have a system, it's called control system, that monitor the transmission, the power that goes through the transmission line. If anything happened, and either by sabotage or act of God, like, we have a high wind in the area, and one of those towers, falls. Because of all these wires are connected, and they're in tension, when one of them falls, it will take like 17, 18 of them down. One after another, like a domino effect, until the cable somewhere snap. So then we have to go and replace all these towers. These are not off-shelf items, because every one of these towers are built for the special terrain. You see a tower that is a little crooked, on the bottom, because it's a hill. You cannot just flatten everything and just build a nice tower. So we gotta just follow the terrain. So every one of them individually